You want to sit that on focus? You can use this to prop it, maybe.
Thank you.
Well, no, I was thinking about leaning it like this. Let me have that.
Hopefully.
Give yourself a break. All right. No questions. How many honestly did the homework? All right. I'm just giving you. You had no problems with it? All right. It was basically how to use functions to either draw things based on functions or describe things by functions. And I have a lot of, I'm going to do a few of these, and I'm going to introduce one other function too. We've talked about the impulse function, the u of t. We talked about the ramp function, right? Then we talked about the pulse functions. Those are the 4 functions we talked about last time, right? Now, there's going to be a 5th function. It's called a triangle function. The symbol for that is this. This is a brand new marker too. This really bothers me. Somebody's going to have to make these markers good. Get good ones. We'll use this. This is a triangle function. And the symbol is this. And tau of t. Now, it's equal to really 1 minus the magnitude of t over of 2t divided by tau times u of, times pulse of t. And where's that? This is in your books. Now, what it looks like is this. It goes from minus tau over 2 to tau over 2, and it has a height of 1. So it's just a triangle. If you look at this, just think about this. This p tau of t here is a pulse function, so it eliminates anything that's outside the range from minus tau over 2 to tau over 2. Everybody with me on that? Now, what this does, if you look at it, let t be 0. The value is 1. You follow me on that? Let t be tau over 2. Tau over 2 times 2 would be just, it's just be tau, right? Divided by tau is 1. 1 minus 1 is 0. So it goes to 0 at the limits. Everybody follow me? This is a triangle function. We'll use this a great deal. Now, some of the things that you're asked to do in the exercises are both draw and derive functions. Draw things based on functions and derive things based on functions. And I have to give you a few. One of them is like this. So if this is 1, and this is going to be the axis t, and this is minus tau over 2. Well, actually, let's do it this way. Make this 5, minus 5, and make this 5. Height of 1, and this is a function, call it f of t. Now I want to define that function based on the functional forms that are available to you. Anybody, it's going to be more than one function, but you obviously see there's a triangle in there. You all see it, right? But the triangle isn't just by itself. It almost looks like, if you think about this, couldn't this be equated to a function where I had basically a square pulse of height 1, and then I'd add to that a function that did this, where this would be minus 1, and these would be the limits 5, minus 5, this is f of t, and this is t, this is t, this would be, or say it's f of t2, this would be f of t1. You all follow me? Now if you add those two together, do you see how it would be that function? The pulse by itself would be here, but when you add the second function to it, it just takes a bite out of it. Follow me? And I'm just going through the progression of things. You could also say if I wanted a function that did this, you have to be able to do these fairly quickly. And the reason I'm saying you have to be able to do them, because you have to do analysis, and the only way you do some analysis you're going to see is you have to be able to define whatever's there in terms of functions. Then with the functions, you'll know certain transforms. Now, this is in the future, but this is the reason these functions are so important. If you can't describe what you see with functions, you can't really analyze it. Remember what I'm telling you. Now, if I had this, something like this, what would you do here differently? What would happen to this function?
Plus 1
Just
plus
flip.
1.
Absolutely flip. Now that function would become this, right? Y'all got that? What if this happens? I gotta make sure people are paying attention to this. I'm gonna do this one down here. That's the triangle function. Suppose I did this. Now I want you to define this function. All right, this is my f of t. How would you define that? Think about what it obviously looks like. What does it look like? The pulse, right? The pulse function. We know that the pulse function, p tau of t, in our book doesn't use this symbol. It uses rect of t over tau, but pulse is the most common symbol used for that. You're going to see this in the journals in a lot of different articles. We know what this looks like. It's basically a pulse, right? Minus tau over 2 to tau over 2 of height 1. That is the pulse function, p tau of t, right? Well, that's the pulse function, but it's shifted, right? So remember how we went through shifting. What do we need to do? We would take the pulse function, and I'm going to show you what I'm talking about. And now the subscript here is the width. What's the width of this class? Just look. 2, right? Now, what do we need this to be? We need this to be 0, the argument here at the center. The center is at 4, you agree? So, and we want, it's a right shift, we want t minus 4. Now, will that do it? How many think it'll do it? All right. With me on this one? If you have questions, ask if you're uncertain about anything. And please try to do the homework every time it's assigned. Don't let it pile up. This stuff will absolutely bury you. I mean, some very good students have had a difficult time in here and failed. So I'm going to warn you about this. If you get behind, you're going to really get hurt, because we're going to cover something today. It's the most difficult topic here. It's called convolution. Once I get done with these functional forms. You all see that right now? All right, that's this. How would you do this function? Are you with me, everybody? I'm going to give you this. I don't want to erase this too. And I'd like to hear somebody give me their ideas on it, because this stuff, there's no one way to describe these things. You're going to see you can do it many, many ways. So now, I want to see how you describe this. Height 2, and this is my f of t. How are you going to describe that? There are probably several ways. Anybody? Somebody could say, well, it looks like a ramp function to start with, that's true, but what would be an easier way? Just think. Think about what I just showed you. What did you say?
Two triangles.
Yeah, sure, that would be the easiest. This, we know that looks like this, right? We know that. So how about we do this one first, right here. How would you describe, what's the width of that, first of all, class? 4, right? So I know I have p of 4, and you can, if you want to put rect, fine, rect t over 4, you can do that, but I like p of tau. Now, where is it centered at, class? 2, so this would be t minus 2, agreed? But I'm not quite done with that part. What's the last thing I need to do to get it right?
The magnitude.
Right, you got to get the scale in front of there, right? 2, right? Now it's right. You've got to be attentive to detail. That will cost you a lot of points. You've got to be attentive to detail. What's the next thing I'm going to do? Well, I'm going to account for the second triangle. That's really, it's not exactly add, but yeah, it is add. But it's a minus 2, right? That's the weight of that one. Minus 2, correct?
Dr. Baginski, why is it just the rectangle? Isn't
Oh, I'm sorry. I put the wrong symbol in there. I wish you'd yell at me. I'm so sorry. My bad. And this would be the same, a triangle function. Still the width is 4, right? Where's that one centered though?
6.
So it's t minus 6, right? That'd be one way to do it. You agree with me? Now, if you want to do it with ramp functions, you could. You could start a ramp here, right? And then you could stop that ramp function there by having a pulse centered at 1, right? Follow me on this one? Then you could start a second, not even a ramp, it would be a ramp with an added value to it here. This would be more difficult. The easy way is with the triangles. All right, I'm gonna tell you that. There's other things you can do, but this is my suggestion. Always go for the easiest way to describe the function with a minimal number of functions. That's probably my advice to everybody. All right, that's that one. She's using my book. In the actual homework I gave you, there were a couple where you had to draw it, weren't there? You did it? Did you have any difficulty with that at all? All right. I'm very pleased, but I usually have people that have questions and concerns. I didn't give you many problems. By the way, did everybody try to get the book? How many have the book now? All right. It's in the bookstores, all right?
It is.
All right. Please make sure you get a copy of the book. That'll be useful to you. One more, and then we'll move on to the topic. I want you to matter of fact, let's do the inverse problem. Suppose my function f of t is equal to minus 2 times u of 5 minus t plus r of t plus 2. And I want you to graph that over the range -5 to 5. So this would be a kind of a problem I'd give you on a quiz. So I want you to graph that. The way you do it is you graph the first part of the function, then the second part, and then you add them together. That's the normal way you do it. So if you're graphing the first part, let's just call this f1 right here of t, and this is the second part, f2 of t. If I'm graphing the first part, what does this look like? Well, it's a u of t for sure, right?
Yes.
Where does it transition or turn on? When t equals?
5.
When t equals 5, right? So we go out there to 5. We know this is the transitional point. Now, if t is less than 5, it is, just make it 0. T is 0, I have u of 5. U of 5 is 1, right? It's on, correct? Anytime there's a positive argument in here, greater than 0, or an even 0, it's 1. The magnitude is -2 though, right?
Mm-hmm.
So that looks like this. It's a curtain. Oh, sorry. Here. -2, right? That's all that function looks like. What about this function? Where does it turn on at? -2, correct, class? It's a ramp function. At -2, it turns on. So this would be -2. And it's a ramp function, and it's good for any value greater than -2. It's going up like this. You all see this, class?
Mm-hmm.
Now you add these two together. So if you added them together, I may not be the best drawer, but I think you can see what I'm doing. From -5 to 5, you can see from -5 to -2, it's just -2, right? Bless you. So it stays there, and then there's -2. And then it's just going to be going up at a rate of, the slope of this is 1 to 1, right? So it's going to go through the 0 point. You all will agree with me there, right? It goes through 0, and then what does it do? It just stays at a straight line and keeps doing this. And the slope of this is 1. So that would be my f of t. Now I ask people to graph these things, and grading on these things is always something where I look to see, first of all, if they've actually sketched two functions properly. If one of them is wrong, then it's obviously going to have a wrong answer. So this would be like 1/3, and that would be the last third of the score, all right? So if you got one part of it right, you get 33%. 2 parts, you get 66. All of it, you get 100%, basically. Follow me on this, class? Yes?
And on there, so it would only be within the range of -5.
Yeah, and I can't ask you to go from -infinity to infinity. You have to give limits when you ask for sketches. Sketches are real important. And I want to tell you one other thing I found out. A lot of people don't have a lot of understanding just how to graph a straight line, how to write an equation for a straight line or a parabola or anything. And you have to know this. If you have any straight line, like if I have this, and I'll just make one up. suppose I have this, and this is 2, and this is -3, right? It's a straight line. And I want an equation for that. Call this t, and call this y of t. Well, any straight line is describable by the slope of the line, so it would be some slope, usually it's labeled m, times the horizontal axis ordinate, which is going to be, in this case, t, plus what's called the the zero intercept, and I'm going to call that b. That's a common way to write an equation for a straight line. Now you fill in the blanks, so to speak. How do you get the value of b? Well, you let t equal 0. When t is 0, you look at the value here. P 0, it's -3. You all see this, class? So that's -3. And now you look at the slope. Well, you'll notice it goes over 2, right? Up 3. So the slope would be 3/2. Do you agree with me, class? So that means this is just going to be 3/2. And that's how you get a straight line equation. You always write the general form, then you observe the value at 0, and you observe the slope of the line. Then you can get the slope by just looking rise over run for a straight line. But I have kids who mess this up all the time. Now, with that, I've had them. I hope this class has nobody like that. If I gave you this, but I said, really, the equation is this. It's 0 for everything until you hit 2. What do you do with that equation to make that right? I mean, to describe that. We've got the straight line. What do we need to do? We need to turn it on for t greater than 2, correct, class? So what do? Anybody? I gave you the function. What's the switching function? Come on, guys. U of t, right?
Mm-hmm.
Isn't that it? We're going to take this whole thing and multiply it by u of t minus 2. Voila. You got me on that? Everybody. That's the simplest way that you can get this. We're going to work on these videos too, so every lecture hopefully we'll be able to put up on, I think you're going to use GroupMe, aren't you? Mm-hmm. Okay. And do you think we can get this done today?
Yes, sir. I sent you the link in the email last night to the group.
Do I have to send this to everybody?
Yes, sir.
I'll do it at the end of class today, and then people can see if they can see it. And I'm thankful for you doing all this. All right, now I want to tell you the descriptors we have: the impulse function, the u of t, the ramp function, the pulse function, and the triangle function are in essence what you really need. You're familiar with sines, cosines, exponentials, but you're not familiar with those bunch that I've went through, and that's the reason I spent some time doing it. In the book, he goes through a lot of examples in the homework, and if you're interested in doing more problems, I'll be happy to give you more problems and their solutions, right? But the ones I give you, I expect you to do because it's the only way to really understand this, is just exposure and doing a lot of problems. Now today, I'm going to talk briefly about energy and power, but you know this already. You're electrical engineers, you just got out of circuits, so it's really almost a no-brainer for you that you've been exposed to this, you know it fairly well. And I'm going to do this in electrical terms. So, if I have a battery here, it's got a voltage here. V of t is equal to 3e to the minus 5t u of t. That's my voltage. And I have a simple resistor here. And make R equal to 2 ohms. And I want to know an equation for the power dissipated as a function of time. So first thing you have to do is, what is power in terms of voltage and resistance? Well, power, P of t, is defined as V of t, this is in the time domain, squared, divided by R. Is it not, class? That's the instantaneous power, V squared over R. It could be V times I, but I is V of t over R, right? Or it could be I squared R. This is the equation we're going to use, and the reason I chose V is because it's given. So now I've got to square that. It's as simple as it looks. I take that and square it, now I get what? 9e to the minus 10t, still times u of t. You all see what I'm doing? Take this, multiply by itself. 3 times 3 is 9. E to the minus 5t times e to the minus 5t is e to the minus 10t. You all get me on this one? Times u of t, because that's when it turns on. Divided by r, it's divided by 2. And that would be the power in watts. I can make this as complicated as I want. I could make this thing times a sine, a cosine. But make it, just multiply it times as many functions as you want. It never changes the essence of what I'm doing. It's always squaring that voltage, dividing by resistance. Now, what is the energy? The energy is a function of time. Well, energy is always power integrated, right? Power is watts, right? Watts is joules per second. If you want energy, it's joules. You integrate power. Watts per second integrated dt gives you joules. And so now I would take the integral, and here it starts at 0, so it can start at 0 here, to t of, and then it would be my p. Technically, I have to make a dummy variable. I'll use tau, d tau here. And that would be the energy. Do you all agree with me there? I think in your book he uses En for energy, but it's obvious if you're integrating power, you're getting energy. Do you agree with me, everyone? All right, what's this going to be? Well, I can take the 9/2 out in front, and now I have the integral of e to the minus 10t, and it's really dt from 0 to t. And instead of t here, I should use tau, my bad. And that would be equal to what? 9/2. E to the minus 10 tau d tau is what? If I integrate that, that brings out 1 over minus 10, right? And then I evaluate it from e to the minus 10t minus 0, but I'll make this a plus there and then just reverse the order. It'll be 1 minus e to the minus t u of t. And that would describe the actual energy that would be what? Dissipated by that resistor as a function of time. Do y'all follow me on this? By the way, what's the total amount of energy dissipated as time goes to infinity? Just look at that. Well, it's really what? 9 divided by 20 joules. Do you all see that, class? As t goes to infinity. At 0, it's 0, right? T equals 0, you got 1 minus 1 is 0. Everybody follow me? That's the relationship, energy and power, in the simplest way. We don't need to go any further than this because you just got done with circuits and you've had all this. You've probably done more problems than you care to think about related to this kind of stuff. All right, then next, after that, we're talking about, the next thing I have to tell you is we're going to be talking in this course about linear time invariant systems. Systems in our case are mainly circuits, right? Primarily, but in some cases you'll be taking a look at a system may mean an antenna communicating with another antenna, but generally speaking, at least for most things in the beginning, we're talking about a circuit, right? Electrical circuits. So when we have a linear time invariant system, the first thing I have to do is define what I mean by that. Linear means this. When I talk about linear, it means if I have some system, and they use a simple block to always define systems. And if I put in some x1 of t, and I get y1 of t out, and if I take another signal plus x2 of t, and I get y2 of t out, well actually, let me not add them together. And I take x2 of t, and I get y2 of t out. Now, so I have one input, doesn't matter what it is, and I get one output that I can track. Another input that I can get another output, right? Well, a linear time invariant system means this, that if I add x1 of t plus x2 of t, in fact, let me do it this way. If I have x1 of t plus x2 of t, then my output will be y1 of t plus y2 of t. Now, and also, if I multiply this one by, say, alpha, then the output here will be multiplied by alpha, and this one by beta, the output here will be multiplied by beta. So a linear time invariant system means simply that if you have a signal, you get an output, you got another signal, you get an output. If you add both of the signals together, the output will be the sum of the two signals. Right? That's what it means, and you can scale that. So an example of a linear system was, if I have, this is my input, inputs are usually called X, and this is what the operation is. Suppose this is going to be 5X will be Y. So my output is 5X. Well, I can tell you it's linear, but here's how you can actually prove it. Let X be 1. If you have 1 there, output is 5, right? Let X be 2. Output is 10. Follow me on this? Add them together. Add them together. If I had 3, output would be 15. It's linear. Follow me on this? You can add the signal's value. And that would be linear. An example of a nonlinear system, and this is the most common one given, would be what if I had, I mean, everybody sees this, right? I go through this fairly quick because to me it's fairly obvious. Most engineers see this stuff in a heartbeat. This is not even a problem. Now, if I do something like this, where instead of having 5X be the operator, suppose I make Y equal to 2X squared. You'll see it's nonlinear. The squaring operation, anything that is something that's going to have a squaring or a higher order operator on there will immediately make it nonlinear, but we'll prove it. If I put 1 in here, I get 2 out, right? If I put 2 in here, I'm going to get 4 times 2 would be 8, correct? Everybody follow me on this? What if I add them together? I get 3 in here. Well, if I have 3 in here, I have 9 times 2 is 18, right? Do these added together give 18? No, it's obviously nonlinear, and that is a test, a simple test, if you're ever wondering. It'll become very obvious to most time. Your circuits are always linear, and they're time invariant. We'll get time invariant in a second. What it means by that is, if you have L, R's, and C's, if your input-output relationship, you got 5 volts in, and you get 3 volts out. If you doubled that input voltage, it went to 10, then you would get 6 volts, guaranteed. If you have any RLC circuit, it works that way. Where things get troubling is when you have transistors that are operating, or diodes. A diode's a good example of a nonlinear system. You all know what a diode is, right? Okay. All right. So that's really just talking about linear systems. Now, what does time invariant mean? This is one that's pretty obvious. Time invariant systems, because we're talking about linear time invariant systems, means this. If I have X of t going into a system, and by the way, the symbol for system operations is given as H of t usually, and we'll be dealing with this, and the output is actually given by Y of t is equal to X of t convolved with H of t, and I'm going to cover that today. You don't know what that operator is, but that's typically a way a system is shown like this. Now, if I have this order of operation, let me go down here, if I have X of t, I have system H of t here, and my output Y of t. If I have X of t minus any constant A, the output will be Y of t minus A. It just shifts the actual point. And what I mean by this is that it doesn't matter the time of day when you put the input. The output is not a function of that. It only is a function as when the actual starting point is. And the output will start, if you have a track of X of t versus Y of t that's done at 3 in the afternoon, if you want to know what happens if you put that same X of t in but start it at 6 in the afternoon, the only thing you have to do is take the Y of t and shift it by the 3 hours. Follow me, guys? Everything is, the input-output relationships are not a function of when you start or stop. It's really t minus A. Follow me on this? This is fairly obvious, I think, to everybody, right? Anyway, if it seems to confuse you, you'll see in the problems that, well, first of all, I'm not going to give you problems with things that aren't time invariant. Not in the beginning, at least. Maybe at the very end of the course you get a little bit of this. But that's that's really basically what I wanted to say, that we're dealing with linear time invariant systems. They're the most common systems. They're also, all your basic circuits with RLs and Cs are linear time invariant systems. And you know the relationship between energy and power. Now we get into convolution. And this is the difficult topic. Please be attentive. I like to do it, I'm not going to do discrete, I'm going to do continuous time convolution first. And I want to tell you one thing. I would appreciate if somebody send me an email to send out this JavaScript that actually shows you how to do convolution graphically. It's a really cool script. But here's what it boils down to. If you have any linear time invariant system, and you put in a delta of t as the input, your output here is called the impulse response, h of t. I want you to just understand that. Input a delta function. I told you we could approximate delta functions. Output h of t is called the impulse response. It makes sense. If an impulse is in, the system is responding to an impulse. It's therefore the impulse response. This is the thing you want. That's the important bit of information about a system. It defines a system, any time invariant system, for all possible inputs. Now, if you have this, it's also linear time invariant. So I have delta of t minus, make it tau here. My output would be h of t minus tau. Does that make sense to everybody? Right? Now, after that, and all right, I'll do it this way. If I scale this, if I put some x of tau right here times delta of t minus tau here, my output would be simply x of tau times h of t minus tau. Do you all agree with me? X of tau could be anything. It could be a constant, it could be a functional form. Doesn't matter. That has to work. That's scaling. This is time invariance, this is scaling. With me? Now, the next thing is, if I take this and if I integrate this, x of tau, delta of t minus tau, d tau, and go from minus infinity to infinity, a linear time invariant system, I didn't say this, but if you do differentiation on the input, you just do differentiation on the output function. Integration on the input, integration on the output for linear time invariant systems. This is important. You can do all manner of linear operations. That's differentiation, scaling or multiplication, integration, anything like that. And you just do them on both sides, input and output. That means on the output, my output here, and now I'm going to call it y of t, would be equal to simply the integral from minus infinity to infinity of x of tau times h of t minus tau, or tau. Yeah, t minus tau, d tau. And this is the definition of convolution right there. Now, you're looking at this and wondering a bit about it, probably. When you do it with discrete time, I better say that for another day, but with discrete time it's a little more obvious. But really what it says is the output of any system can be gotten by taking the input, replacing t by a dummy variable, in this case tau. You can use lambda if you like lambda. It's any dummy variable, dummy meaning we integrate it out. It's not there after the integration is done. Times h of t minus tau d tau. Got to tell you a few other things about convolution. And I'm going to give you some examples, and you're going to be probably a bit puzzled by some of this stuff, but it'll become clear. The more problems you do, the clearer it gets. When you have convolution, y of t is equal to, it can be x of t convolved, that's the symbol for convolution, an asterisk, with h of t, or it can be h of t convolved with x of t. That's a symbol for convolution. And what that means is the order that this is, you could put h of tau here and x of t minus tau. This is all could be equal, and go minus infinity to infinity of x of tau times h of t minus tau d tau. Or it could be the integral from minus infinity to infinity of h of tau times x of t minus tau d tau. Either one will work. Now the best thing to do is give you some examples so you can actually see it. I'm going to show you the graphical method that is best to do this by. So I want you to be attentive in my next one. By the way, we're supposed to get some really bad weather this week, aren't we? Anything later today or not?
No.
Maybe
They
like
did
tomorrow.
not eat, like,
It's gonna start this tomorrow morning.
They're probably gonna send out the warning during the game, if there is one, which is stupid. The university didn't think it through very well.
I want to go to that game. This is the Georgia basketball game I think you're talking about, right?
Yeah.
Yeah, and I got tickets. I mean, what are you gonna do if there's a tornado? That's a tornado shelter, right?
It's not gonna fit 10,000 people
Huh?
though, cause not the whole arena isn't a shelter. There's
isn't?
gonna be like 10,000 people there now. The upper part isn't.
Said between 2 and 8 p.m. It's supposed to be our severe window.
Yeah, but the game starts at 5.
Yeah.
There you go. I didn't know.
So you think Tal's bad by 2?
I was at a football game years ago when we were playing, it was West Virginia, and they had a back. His name was, was it Noel Devine? He's a real, he was he'd call him a Smurf. He's short and unbelievable. And were you at that game? That was the rainiest, worst day of my life in that stadium. It was an absolute nightmare. I've never been that wet in that stadium ever. I never want to be there again. Anyway, for that kind of a game. Noel Devine, that was the guy's name. That guy is unreal. Anyway, so here's some examples to try to make it real. And I want to tell you that, I'll show you the trick on this one, but I'm going to give you some simple examples. So I'm going to have one function, x of t, and it's going to be a simple one. That's going to be a pulse. Now, pulse might actually confuse you a little more. It's going to be simply u of t, right? And my second function, h of t, which is the impulse response, I'm going to make this equal to a pulse function of width 2 of t. All right, so here's the way you do convolution. The one that has the most change is the one that you're not going to, I call it flip and shift, you're not going to move around. You see that x of tau? That's simply replacing the variable t with tau, right? When I look at these two things, this is my opinion, the thing that has the most change is this, all right? That has the most change going on because it goes up and then down. The u of t just goes up and stays up. Follow me on this one? So for this function, this is the one I'm not going to flip and shift, and you'll see what I mean by it. It means it's going to be the one that is going to be the x tau. It's going to be the first function. And what I do is this. I start, and now I just graph my x of tau. And I'm making that equal to, now this might be a little confusing. This I'll make x, and I'll make this h, just because I want to make it as simple as possible. So this one looks like, if I look at this, it looks like this. It's -1 to 1, has a height 1. This axis is tau. Does everybody see that? I've simply replaced t by tau. This is the one that I'm not going to have any crazy argument here. Now the next thing I do, and when you're starting this, is I'm going to take my second function here, right here, and I make the argument p2 of minus tau. Now one thing you notice about, I make h, not the p, I make this u of t equal to u of minus tau. You see how there's a minus tau in there, everybody? But let t be 0 for starters. So what does that look like? Well, this is going to be my h of minus tau, which is really u of minus tau. What does that look like? You have to graph it versus tau. Class? Is it on down here? Is it 1 or 0 back here?
2.
See the minus? It's 1, right? It starts as 1, and it goes down to 0. Because anytime that argument is negative, right, it's off. Anytime it's positive, it's on, or its value is 1. I call it a switch. Everybody see this, class? All right, so this is u of minus tau right here. The axis is tau. Now the next thing we do is we take a look at the area of overlap. You can see that this function and this function overlap between -1 and 1. Do you all see that? Now if they do, then I need to start this function further back. Are you with me? And the way I do that is now I say this function is going to have the argument u of t minus tau here, but what I'm going to do is make this condition. I'm going to say this will be true for t. If I want this to be 0, I want t minus tau to equal 0 when when tau is -1. So I have -1 minus tau equals 0. It means that I said that wrong. T minus tau equals 0. That's this argument. And this occurs when tau is -1, so it's t minus -1 is 0, so it's t plus 1 equals 0. So that would be t equals -1. What that means, the reason I'm saying this, is now for t less than -1, there's no overlap. Remember I said it was like drawing a curtain here the other day? Well, for t equals when I take a look at this, when t is less than -1, then when these two are multiplied together, there's no area of overlap. It's just 0. Got me on that? But now we're going to say this. This is going to be for t greater than -1 and less than 1. And what's happening here, and you'll see this in a second, now I'm going to say that now I'm going to have an area of overlap between these two functions where I have this and this. Can you all see that there, class? Just take a look. Now, look what it says to do. It says to integrate these two functions, d tau, right, after they're multiplied together, right? And here's the thing, there will be, because our integration was with respect to tau, this gets a little confusing, but what you have to do is take a look at the different points in time where there'll be different areas of overlap. You all see between here and here, we're just drawing the curtain, so it's pretty clear how to write that expression, right? I can say for this range right here, this time, matter of fact, we'll do it this way. We can say the convolution of the two, or we can call it y of t equals x of t convolved with h of t. We can say y of t equals 0 for t less than -1, and then y of t equals, now we do the integral, right? When we take a look at this, it's the integral, remember that's tau, from -1 to t, right? And the function, well, when we multiply 1 by 1, we get 1, right? D tau. And that's simply tau, right? Evaluated from -1 to t, which is equal to t plus 1. This is what the output would be. And this would be true for t greater than -1, less than 1. Can you all see that, class? How many see this right here? You're not used to doing this kind of crazy integrations right here. But if you think about it, this is just the two functions are multiplied together, and that's what you're getting. You all see this? How many see this right here? All right. You having problems? What don't you see? That's the best question. Can I help? I mean, if you realize we're just multiplying two functions together, right? The problem is they have to be non-zero at both at the same time. I say it's an area of overlap. So you have to look for points where both this function and this function on the axis tau are overlapping with non-zero values. And then you multiply those together and then integrate that over that, right? That's what it says up there. So that's t plus 1 would be the value from -1 to +1. But what happens, what would y of t be, the convolution of those, for t greater than 1? Now just take a look at that. Remember, the point right here is what? That's t, isn't it, right? So what happens when t gets greater than 1? Now just take a look. Isn't this still overlapping? Right? But no matter how far out I go, do I ever get more area of overlap? No, as a matter of fact, that's what it does. What it means is the convolution of those two things will just be the area of here, it would be 1 times 1 integrated from -1 to +1 or 2. Follow me? So here it will be just 2, and that would be true for t greater than 1. Now, if you were to graphically show that convolution, it would look like this, and I'll do it right here. Now, if this is t, remember, at -1 is when it starts, right? And here, it's going up linearly, right? And it's going to go to a value of 2. And then at 1, from here on, it just stays there. So that would be the convolution of those two functions. This takes some time. The thing that will bother you the most is this, right here. I promise you it will. We're going to do another one, and you have to do a lot of these to understand this, because people blow this all the time. When I say 3 hours on it, I mean at least 3 hours, at least. I'll do some more. I'll say one other thing too. Signals and systems is probably the most important class that you take for all upper level courses, because in electrical engineering, this stuff is what is the basis for almost everything we do. Your circuits in this course. Now, on to the next thing. Staying on this topic of convolution, remember, I'm going to put down equals the integral of x of tau times h of t minus tau, d tau, from minus infinity to infinity. That's the definition of convolution. Now I'm going to go through, give you a couple other functions. Suppose I give you x of t, matter of fact, let me just draw them, because this is the way a lot of times it's done, and you have to find an expression. Actually, you don't have to find an expression for this one, because this is graphical convolution. I'm going to have two functions. The first function is going to be make it 5e to the minus t u of t. So that starts at 5, right? And it just exponentially decays versus t. And the function I want convolved with it is this. 1, height 2. So this is going to be my h of t. Now remember, it doesn't matter which one you flip and shift and which one I say flip and shift, because whenever this is, remember how when we did this we had h of minus tau was literally flipping it around the axis? Do you all remember this class? So when I say flip and shift, I'm always talking about this function, because that's literally what we do. When we take a look at this, I'm just going to tell you, this has got this is a lot more going on with this one, all right? So you leave that alone, that's going to be your x of tau, and you draw that. Just draw it on the board. I mean, draw it in your paper. This is tau now, and this is my x of tau, which is equal to 5e to the minus t, tau, u of tau. And it looks like this. Right? Now the next function, first, if this is h of t, I need h of minus tau. That's flipping it about the axis. The only thing you do is take this, and I say flip and shift, but I guess I should have been more clear. Flip it like that. You just rotate it around the stem, right? The y-axis in this case, or whatever axis that is, and just rotate it and wrap it around. That's flip, and then you shift it by adding time to it, right? You add t in there. Now, this is at 0. As you see here, if I add time, t in here, it's going to start moving it this way. It draws a curtain that way. You all with me on that? And you can see at 0, there's just starting the overlap, right? So one thing you can say for sure, the convolution of these two functions, y of t, if they are convolved, x of t convolved with h of t, that y of t is 0 for t less than 0. That won't be the case always, but you all agree with me, right? Now, once it gets a little greater, when t all of a sudden is a little greater than 0, when I have t minus tau, I've got to put some limits on this. Here's t, but the back end of this, when I look at that, that has a width of 1, so this is going to be just t minus 1, right? You all agree with that? Now you can see this is where they overlap, right? So you have to take the product of this function times that function and integrate it over that. And you can see if I wanted to draw it down here, it really looks like this, right? That's the function, which would be 5 times 2, or it would be 10e to the minus tau, right? And it would start at 0 and go to t, and I'd have to integrate that. Do you all agree with that, class? Right? So now I could say my y of t would be equal to the integral, and it would be from 0 to t of 10 times minus tau d tau. And if you take a look at that, that's going to be 10 over minus 1, evaluated between 0 and t, or it's really 10 times 1 minus e to the minus t. And that's true for t greater than 0, but less than, think about it. What happens when t goes to 1? Then the whole thing is now inside, right? It's all in there, right? It's moved through. Any further movement, the integration would, the lower limit wouldn't be 0. It would be t minus 1 to t. Follow me? So this is going to be true for 0 to 1. All right? How many see this part? Y'all see what I'm doing? Guys, I mean, do you see it or not? Just level with me. All right? You see it? Okay. I'm trying to get a read on you guys. You guys see it? Okay. I'll level with you. It's tough. You may look at it in class and nod your head, yeah, I get it. Make sure you do the problems. It gets very, very confusing. Now, what happens when t is greater than 1? Well, if you take a look at that, it's going to be this form of the integral, right? It would still be 10 minus tau d tau. But look what happens. Now, just erase that whole thing. Am I over? Oh, I am. Sorry. T minus 1 to t. Now what happens is the lower limit is t minus 1, and this is t. Follow me? And you do that integration, then you do the evaluation. And that would be for t greater than 1. But you all see the pattern here, right? The one that's got the most going on, you don't flip it or shift it. You leave it and just change the axis to x, make it a tau variable. The one that's got the least going on, you flip and see if there's overlap. If there's not, move that. You have to add that time operator until they start overlapping, and then multiply the two functions together and integrate them. I'm going to give you some problems. This is the toughest topic here. I'm being honest with you. You've never done this kind of stuff before. Yeah.
You get that 10 because you multiply them when
What's
you
it?
integrate it. You get that 10 because you multiply when you integrate it.
Yeah, well, there's a 2 there and a 5. That's where the 10 comes from. I did that on purpose because I want to make people attentive to the magnitude. Sometimes they get sloppy on. All right? If you've got questions, see me afterwards. I appreciate you doing the homework for Monday. Please do this homework. And labs start next week.